And we will move on to Matt. Matt, whenever you're ready.
All right, thank you very much, Noelle. Good to see everybody again. Well, those of you that I've seen before. My name is Matt Patterson. I am a machine learning engineer in Santa Cruz, California, in an internship. Currently working on a project in reinforcement learning with traffic controls. My capstone that I'm excited to share with you guys is about outer space. Now I'm kind of super into exoplanets. I'm gonna go ahead and share my screen with you. There it is. I did my project about the Kepler Objects of Interest dataset. For those of you who are somewhat space geeks like me, you might be familiar with the Kepler Space Telescope. This was a telescope that was launched back in 2009 to take pictures of deep space, and it actually is in orbit around the sun, just like Earth. It's in Earth's orbit, as opposed to orbiting Earth. The idea is that it can see this same place in the sky for a long time without having Earth get in its way. And so what we did was we took and created a data set. We called it the Kepler Objects of Interest dataset, and NASA and Caltech had scientists who worked really hard to basically look at these satellite pictures and determine which one of them, or which one of these stars had a planet going around it. So the data science problem when it comes to this is that data astronomy is really time consuming. It's expensive because it costs a lot of money for these very well-learned people. They take really long observations of stars. In fact, some of them, you only see the exoplanets cross once every year. And they have to do this by, well, you can't even see the planets themselves from Earth. So they create what are called light curves by observing the intensity of the light coming from the planet and then charting that on a time series. So we've gained the ability to compile a vast amount of data, and now we've gained the computing power to actually analyze it with computers. A little background about the data set is, this Kepler spacecraft was launched back in 2009. It took a year and a half, or more than a year and a half, to get its first exoplanet confirmed in December of 2011. And the NASA spacecraft has since been able to discover over 2,600 of these exoplanets, which I think is super cool. The other cool things, if you're kind of geeky like me, is there's only one telescope on this whole thing, and it's always pointed at the Summer Triangle. The Summer Triangle is this constellation that I kind of like because it's so simple. It's just 3 really bright stars that make a triangle, but it's representative of the Cygnus and the Lyra constellations, as well as Aquila. But the Cygnus Lyra, this is like really the general area where Kepler was pointed for its whole life. So the data science solution to this data science problem is that we can compare the data of the currently confirmed and unconfirmed planets. I mentioned that there were 2,600, now there's more than that, confirmed exoplanet observations. There's also a number of confirmed to be not exoplanets. And we can use that as our training data to train a model to look at that same data set and then decide of the unclassified observations, which ones are actually planets and which ones are not planets. We can then package this into a Python program or something and use it to identify planets on the TESS mission. TESS is another satellite that was launched by NASA back in 2018, do the same thing, but in different parts of the sky. I was actually fortunate enough when I was doing this project to speak with a NASA scientist named Dr. Jessie Christensen. She's been working for Caltech and NASA since the beginning of the Kepler project. So she's been working on Kepler from its start. And I asked her how they classify which of these 10,000 observations that Kepler's put together, and then more than that in the K2 mission, and then even more than that in the TESS mission, and how they decide which one of these to focus all of their time and resources on to choosing which one's going to be an exoplanet. And she said, well, we use this thing called Eddie Vedder. It's really called Eddie Vedder. It's a Python package, it's a rubric, it's not machine learning, and they put the data through it and it vets it out. But she said there's nothing like that for TESS. So if my model works, maybe I can be the next Eddie Vedder. The KOI data table, the Objects of Interest table, was last updated in 2018. That's when the Kepler project kind of ran out of gas. As I mentioned, it contains nearly 10,000 observations. Each of the observations requires a minimum of 3 transits in front of the star. So the point of this is that this data set these are observations that NASA scientists are they feel pretty good about the fact that there probably is going to be a planet there. There's 69 columns of data, so 69, components that I've whittled down to 35 features to use in the model. Of all of the roughly 10,000 observations, I actually culled just over 1,300 of them, or just under 13, to get rid of nulls, get rid of non-numeric values, things that I couldn't impute the information into. Thought it better off just to drop them, which left us with about 8,700 observations. Of those, 4,200 have been certified by NASA and Caltech to not be exoplanets. And there's 2,245 unknowns, which leaves us with a baseline stratification of 35% positives and 65% negatives. So if we were just to guess that every object on this whole thing was not a planet, we would be correct 65% of the time. The strongest features that are strongest correlated to our KOI disposition, or yes, it's an exoplanet, or no, it's not an exoplanet, are the disqualification flags, which we'll talk about in a second, the uncertainty of the measurements, as well as gravity and temperature around stars and the possible exoplanets. This is a correlation matrix heat map of the disqualifier flags. These are the strongest correlated features to whether or not this observation is a planet. And all of these are negative correlations. Now, what's interesting, or I guess obvious, is that each of these flags were created by the NASA scientists as a way to disqualify the planets. So if they decided that there was a reason for this to not be an exoplanet, they gave it, points, so there were numerical value associated with it. So essentially, these are useless in the idea of making a model, because a self-fulfilling model is just bad. You can't create a predictive model and use inputs that are predictive disqualifiers to the same classification. So I've gone ahead and dropped all of those flags out. We've also dropped other non-empirical data, such as ID numbers. In this case, there wasn't a lot of feature engineering that I wanted to do, because the rest of the data was actually pretty good. So let's go ahead and take a look at the other strong correlations. This is the next strongest, which is still not very strong, but it's the uncertainty in the measurement of the photospheric temperature of a star, which is the temperature basically at the surface of the star. And the estimated temperature, it's going to have a margin of error. So the uncertainty here, I've plotted the absolute value of. The positive uncertainties in the y-axis, the negative is on the x-axis. And as you can see, the orange dots, or the number 1 out of the binary classification, this is where we are pretty sure there's planets. This is from the training set where the NASA scientists have said there's definitely an exoplanet there. And all of those are clustered close to 0, 0, so close to certain or no uncertainty. The same can be seen in the uncertainty of acceleration due to gravity at the surface of the star. I found it really uncanny or interesting that these are just measurements. It's the uncertainty of the measurement as opposed to the actual gravity in this case, or the temperature. And I saw the same thing here on the hours of duration. And this is what really made the light bulb go off. We are uncertain about how long a transit is going in front of the star. We're uncertain about how much time we can see this thing before it goes away. So how certain are we that there's even anything there at all? That is kind of the logic that it follows. And when I was talking with Dr. Christensen, she said that they started out before Eddie Vedder by just picking which star has the most brightness and which light curve is the most pronounced. Because obviously the most you can see it, the more likely you can predict it. So obviously, those are going to be the strongest correlations. When we look at the other correlations, the actual measurement of the actual expected gravity, in this case of near the star, we've got much bigger ones, much bigger stars with much more gravity, much more density really is what's creating that gravity, are going to be suggestive of there actually being a planet. Predicted equilibrium temperature or basically how hot is this possible exoplanet. We see below 4,000 Kelvin to be really falling in that sweet spot, which also makes sense. We're trying to find possible planets that possibly might be able to foster life. So they're going to be a certain distance from their star to keep them in an area that may have water ever sometimes exist on the planet. it's a lot of unknowns. You know, solar predictive temperature, again, if the star we think is more than 8,000 Kelvin, that's really, really super hot. Probably not going to allow anything to be alive near there, and maybe not even solid. So that was the data set. Now we're going to take a look at the model. This is a model of the Kepler satellite. I wish I could say that I drew it. Doesn't really matter. These are the models that I drew. I put together two logistic regression models, one with a very limited data set. That's the one on the right. These are the strongest correlations. And the one on the left is the most data set, basically all the features left after the ones I dropped off. And my model was 91% accurate. So we just raised from the baseline of 65%, we raised that accuracy score up to 91%, which I think is pretty good. The confusion matrix, this is what's labeled here, shows us in the top left our specificity, or the total number of true negatives over all the negatives. In this case, that's 93%. So we had just over 10% of the things we predicted to be false were actually exoplanets. On the bottom right, we see the number of true positives that we had, that we predicted to be exoplanets in our training data, and actually are exoplanets in our training data. So we're 89% true there, just a little bit more than 7% false positive rate, which again is good. I'd like there to be 0 false positives, because if we're going to send people on a 60,000 year journey all the way up to the Cygnus Lyra constellations, I don't want them to get there and see that there's no planet after all. So later on, I will show you how I employed this function that I wrote. I have a library that I created in Python called Lebowski, reference this dude, and I created a function called tell the truth. So you just call dude tell the truth, and you put in your parameters. In this case, the parameters, you know, they are the model and the data set. And what you're looking at here is the logit function. I'm not sure if Noelle's going over this with you guys yet, but in simplest forms, if the model is 50% certain or more that this thing is likely going to be classified as an exoplanet, then it classifies it as an exoplanet. If it's less than 50%, then it doesn't, which leaves us with those false positives. So if I created this function, tell the truth, to raise the threshold from 50% up. When I went to 75%, I lost half the false positives in training data. I actually ended up going to 99% to eliminate all the false positives, which was really cool. Before I got there, I employed 2 more models. The one on the left, this is another confusion matrix, shows the Random Forest Classifier. And this is a decision tree model that employs bagging or bootstrapping aggregate. You know, the point is it's a lot more accurate than in this case, than the logistic regression function, not in every case. But you see that it improved our specificity. We've got 95% specificity and 92% sensitivity, so fewer false positives than we did before, which is really great. I get a little bit nervous though when I see really great accuracy scores. So I put all of this into a recurrent neural network. Charlie Rice from General Assembly mentioned that if you're going to create a neural network with only 10,000 rows of data, it's kind of like using the sandblaster to cut a salt cracker. It's really overkill. But what it did well for me was it really reaffirmed the results I got from my Random Forest Classifier. So I felt more confident about my predictions. As you can see on the right, it's not in a confusion matrix. It actually shows the trajectory of our training accuracy and our validation accuracy on an XY axis. The x-axis here being the number of epochs it ran through, and the y-axis being the percentage of accuracy. And you know, we came out with a 95% accuracy, 92% sensitivity, and a 96% specificity. So it only got better. So what does this tell us? Is there anybody out there? Did we find an exoplanet? These unfortunately aren't actual photographs. There aren't renderings of actual exoplanets done by NASA. We can't actually see these, so they're all artist renderings. So here's the models. I put together this ensemble. I've got about 90% accuracy or more in each one, around 90% sensitivity, 93 to 96% specificity, and they each predict a different number of planets. So I created an algorithm that takes each of the results of each model, and if each model says that this particular object of interest is a planet, then it, you know, spits out yes on the algorithm that this is a planet. That left us with 664 exoplanets that with 90 to 95% certainty we are sure are planets. which is cool because now that we know there's 630 planets on this out of these 2,245 that are going to be there. The problem is I still don't know exactly which ones are there. So finally, I used Dude, Tell the Truth and raised that ambit or limit to 99%. And I discovered 39 exoplanets. I shouldn't say I discovered. NASA and Caltech discovered, and I identified from their hard work 39 definite exoplanets. And so the next steps is to package this algorithm up into a cool Python, program, make it accessible, open source it, put it on GitHub, and hopefully be the next Eddie Vedder. But more importantly, I would like to introduce to you SumNiva. I took one of these planets that I'm pretty positive I just discovered. I named it after my partner, Summer Nicole Van Slager. Sometimes people call her SumNiva for short. This planet is a roughly 3/4 of an AU away from its star, or 3/4 of the distance that Earth is from the sun. Their star is about 90% the size of ours, and its size is roughly 3 times the size of Earth. The planet is at Kepler ID 5709725, so you can find it on the Kepler Objects of Interest dataset. And if you have a telescope, you can pop in Declination 40.934769 and write Ascension 293.123410. And for 7.5 hours at a time, every 86.5 days, you can see maybe SumNiva. So that's what we were able to do with exoplanets. I know that we're not going to take questions until later. Tiny little excerpt of Do Tell the Truth. I'm totally a Lebowski fan, and I hope you are too. Go planets. And thank you, everybody. Appreciate you coming.
Awesome. Thanks, Matt. Awesome job. We all would be so lucky to have our partners name an exoplanet after us. So that's incredible. With that, go ahead and post your questions for Matt on Slack. And